Good afternoon, everyone, and welcome to our webinar for today, the eGPS200. We're glad you were all able to join us. I know we've got a few people still calling in, but we'll go ahead and get started, and they can obviously join as they get fully connected. Our presenter today is Dave Gallup. Dave has been with Somat for 20 years and is currently working as the eDAQ product manager. So he helped get this product off the shelf and running and is going to tell us more about it today. Dave, it's all yours.
Thank you, Krista. I hope everybody can hear me okay. If anybody can't hear me, I'm afraid you're going to have to tell us at the end, so I apologize for that, but let's get started. So this is really about introducing the new eGPS200, which is a GPS-based RTK system. This has been added to our product family to provide us with a very rugged and robust field-ready system that can be used in any environment and provide very accurate measurements no matter what the situation that you're in. A little bit of an update on the HBM part of the company here. Our philosophy is we want to accelerate the competitive advantage for our customers, and we do that by covering almost every facet of testing and to some degree production. So we have software that would work directly with FEA packages for our design components. We have test systems such as our eDAQ, the MGC, the Quantum, for our lab testing, field testing, even production line monitoring, and then of course into the manufacturing with devices such as our PMX system, which is our all new control hardware that interfaces with our new PMX software. So our philosophy is your partner for optimizing product lifecycle performance is our little catchphrase here. So what the purpose of this is to introduce everybody to the RTK-based eGPS200 and the eGPS200. And this is a global positioning system that's specifically designed for eDAQ. So this is something that we've designed that's really around the philosophy of producing a piece of equipment that is genuinely plug and play to be used with an eDAQ data acquisition system or an eDAQ Lite data acquisition system. So quick look at what we're going to be covering in this very short webinar. Quick review of the purpose of the device. Where is it from? What does it do? Look at the specifications for it so you can get a feel for its level of accuracy and its usefulness to you. And then the all-important part, the installation using this as an eDAQ, and this will encapsulate all aspects of the RTK-based one, which is a little bit more in-depth than the standard GPS, so there's a little bit more to it. Some simple data handling just so you can get a feel for what you can do with the data afterwards, and correlation of data types, what the meaningful parts of this are, and then a very brief look at some applications such as brake testing applications. So the pictures that you can see on the screen here, we have one that's a mounted system on a plate that was actually inside a Honda Odyssey owned by one of our engineers, Brian Lovedoll, and then here we see Dennis Dittmer's truck that we was using for checking the accuracy level using a Bosch radar, and you can see the plate here for the investigation of the accuracy of the speed, such like. So we've gone to great lengths to make sure that this is appropriate for what we're really hoping you'll use it for. Just a quick look at some of the historical kind of lead up to this, and obviously the most important thing was when we went out and tested, we had a pretty good idea where we were, but we oftentimes didn't know exactly where we were, and this is very important, particularly when you're doing different surfaces. Whilst we can say, yes, we were on this rumble strip, we were on that offset sign, it's sometimes much more beneficial to know exactly whereabouts you were on it, and if you'd crept off of it to some degree. So knowing where you are, having a good idea which one of those two makes sense, well, you can see the early iterations of some of the situational awareness systems, if you will, that were used in some of the earlier testing. Keeping a log was one thing that people did, and of course keeping a log isn't a bad idea if that's all you've got. But of course the most practical solution is having the information recorded automatically for you so that you don't have that interruption. In fact, to a large degree, you could set this system up in such a way that it could record data given a proximity location. And the thing to keep in mind is that integrated solutions are always easier and generally better to use. When you have to use external systems, they can become cumbersome, complicated, and difficult to use. The problem with measurements is they happen anywhere, anytime, almost any place. And of course, having the ability to do this fairly quickly and easily is something that's not going to encroach on the testing sequence. And so this has become recognized as a leading rapid deployment GPS solution. Many already existing users of this system say that one of the facets of the system that they particularly like is the fact that it's very, very easy to use, very user-friendly, and can be deployed in a very, very short period of time. We haven't figured out yet, as Walt pointed out earlier on, where we need to put the antennas for the RTK version on the motorcycle. I'm sure the rider wouldn't like them on the helmet, but if anybody has some suggestions, perhaps you could make them at the end. The challenges of data and correlation of data. The challenge of correlating data isn't just knowing what was happening, but knowing where it happened. So having some information about a positional reference, as this example here shows, this is actually from the Swiss military testing area, and this is a section of data that correlates to a particular point within that series, which can be clearly seen on the GPS overlaid map, and here would be the dynamic data that's associated with that particular event. So GPS information goes a long way to answering these. Sometimes more is needed, and that's really where the RTK component comes into play. Inertial measurements are all about knowing the behavior of the vehicle dynamically, knowing whether or not the vehicle is in a pitch, or if the vehicle is in a roll, or if there is even a yaw component to the action of the vehicle. Knowing this information is very critical. As the mass moves around, you need to know how it's behaving on unsprung and sprung mass locations, and this is the perfect way to get that from the point of view of a positional reference within the vehicle. So this particular device, the EGPS200, is a very, very efficient and very quick way of getting this kind of information with a very high degree of accuracy. Not only is the GPS data particularly useful, but also knowing that dynamic component is incredibly useful, especially when you're doing performance or brake testing. This is the most critical component in this, is actually understanding the behavior of the vehicle and those mass moments as the different track events occur. As you can see, the system is fairly compact. It's very small. It's only 135 millimeters in width, and 40 millimeters in depth, and 215 millimeters in length, and it weighs less than 1.5 kilograms. 1.5 kilograms is about 3 pounds. So it's actually quite a lightweight, very compact, but as you can see, very rugged, as per our normal philosophy of making them built to last design. This one is part of the family. Specification-wise, there are two significant types to the eGPS range. There is the EGPS200 and the EGPS200 Plus. And the only real differentiator between the two is the antenna plugs. With the EGPS200 Plus, you have the secondary antenna, which gives you a differential for your GPS signal as well. So specification-wise, you've already seen the dimensions, you've seen the weight. The operating range fits very nicely into our traditional range of operating temperatures. Power is provided directly from the eDAQ. There is no requirement to provide power to this unit from any other external source. It comes directly from the ECOM and the ELCOM layer, as you'll see very shortly. And as you can see, the accuracies are undeniably very, very good for a GPS-based RTK system. We'll go through this a little bit later on in a little bit more detail, just to explain some of the components that are described here. So here, the IMU gyroscope sensitivity, as you can see, it's very sensitive. Temperature coefficients, all of those are measurements, so you know exactly what the implication is. And the bias, as well as noise, frequency response, all the accelerometers are at 300 hertz, by the way, and accelerometer sensitivity, as well as the bias, the noise performance of the accelerometers, and the frequency response of the accelerometers. So as you'll see from the specification, it's a very capable unit. This illustration here alludes to some of the requirements that are needed in order to successfully use this device. This is just the base footprint of it, just to reiterate the shape and size and dimensions. And you'll see that these are the base channels in the system. You have a trigger channel, obviously your standard GPS channels, as well as a 200 Hertz 3D speed, a 20 Hertz 2D, and a 20 Hertz 3D. Heading, very accurate heading measurement, as you'll see in a moment. Gradient, so you actually know the component for the pitch, the accelerations, and then of course the standard GPS components such as time references and the number of satellites. On the Plus package that includes the dual antennas, you now have yaw, pitch and roll rates at 200 Hertz. These are derived to some degree from the acceleration measurements. And then you also have the RTK yaw as well as pitch and a baseline and accuracy for the RTK component as well. So just to summarize the accuracy component of this, as with all satellite GPS systems, the maximum number of visible satellites covers approximately 180 degrees in the horizontal plane, but only 90 degrees in the vertical plane. As you can see here, there will always be a much, much more accurate reference for the horizontal measurement than in the vertical measurement, so altitude is always problematic. Typically, calibration using barometers might be recommended from time to time just to be absolutely sure that everything is lining up correctly. But if we look at the actual GPS component here, the GPS is accurate to about 3 meters. It's a little bit less than the picture you see here of this parking lot. The acceleration is 0.5% of full scale, and the heading is 0.05 degrees at 10 milliseconds. So you can see that these are pretty accurate measurements that are coming from this unit. And it does not require a base station. It doesn't use the base station. Now, some of the implications of this, of course, when you are static, that you get a limited amount of stationary noise, which means you get a little bit of creep around, if you will, of the signal. So, as you can see here, the speed here in meters per second, you've got all of the trigger thresholds that would be required for doing things like brake testing and performance testing. There isn't a problem with this. When we look at the acceleration and the noise level of the acceleration, you can see, to coin a very popular phrase, it's in the weeds. And when we do comparisons of the vehicle speed versus accuracy of count position for triggers, as you can see, typically we get extremely accurate measurements. By the specification for the brake requirements for both the federal requirements as well as international requirements, these are well within the boundaries of the acceptable ranges. So how do we get this to the eDAQ? Well, the eDAQ, all it needs is we need a COM layer, and the COM layer needs to have the GPS port on it, obviously. It's very important to note that the eGPS200 does not work on the DIO layer. So don't go trying to plug this into the GPS on the DIO layer. It only fits onto the COM layer. This is the ELCOM. This is the ECOM layer. And there's the GPS input on the ECOM layer with the 3 cans and the VBM. Here's the 3 cans and the VBM. Sorry, these are the 3 cans. This is the VBM. You don't need any special software, no special adapters. That comes with the cable that you need to plug to the eDAQ. The eDAQ provides all the power that it needs to the eGPS200. It's all there. So one cable, Turk to Turk, connects the 2 devices together. What could be easier? So a couple of things to make note of. The unit has markings for orientation. You'll see this very clearly on the unit that there is a direction of travel pointer on here. Whilst trying to get close to the center of gravity is obviously of great benefit, it isn't absolutely essential, but the gyro measurements will clearly be a lot more accurate in reference to center of gravity if it's close to the center of gravity. Then we need to attach 2 antennas. These are the differential antennas. So we're looking at the eGPS200 Plus here, and they need to be set 800 millimeters apart, and there is a nice guide provided. Once these are set 800 millimeters apart, with the cable direction in the correct direction and the orientation of the GPS receivers in the correct direction, we're ready to move to the next step. So number 1, GPS antenna number 1 is trailing as far as direction is concerned. GPS number 2 is leading, and the cables are towards the direction of travel. Once you've got these set up, and these could be on anything, you could put magnetic mounts on there, or you could use an adhesive, keeping in mind that when you use adhesives, if you put this into a location that might be in a thermally subjected, high temperature subjected area, that it's possible that the adhesive may fail, so you really don't want to take any chances. Try and avoid the areas that might happen in. But then just plug these in to the two antenna ports, antenna 1 on the left, antenna 2 on the right. Plug them into the eGPS200. This is the best sequencer. Plug them into the GPS200. This would be inside the vehicle with the front of the vehicle over here and the rear of the vehicle over here. Once you've done that, it's a good idea to make sure the eDAQ is switched off, although you can cycle power afterwards, but plug it into your eDAQ. Plug it in via COM1 on the back of the eGPS200, and then into the GPS port on your COM layer. Power your eDAQ up, and you should get, once you've powered your eDAQ up, you should get a power LED illuminate on the front of the eGPS200. If the power LED doesn't illuminate, check the cable. That's the highest probability of the problem. Second probability or possibility is you've not got enough power into the eDAQ itself, so it can't provide enough power through to the eGPS200. So, green LED is on. This is your layout thus far. We've got the two antennas attached, number 1 and number 2, the power into the eDAQ, and now we have a green LED on to indicate that we're all powered up and ready to go. This isn't a very eloquent solution. It doesn't look very eloquent, but it functionally works. This is down with some Velcro. It would be much better if you want to get very accurate measurements to mount this very securely onto the frame of the vehicle or onto a point where you know that you've got direct contact with the sprung component of the vehicle. So make sure it's in the correct orientation, the direction of travel. This is the arrow at the back here. You can see it zoomed in on here. Direction of travel, indicating that it needs to be that way for the front of the vehicle, and as you can see by the seat here, that the front of the vehicle is indeed that way. The antennas already mounted 800 millimeters apart. In this example, I just put them on a piece of wood, glued them down onto the wood, and then I screwed and clipped the wood to the rail on the back of my truck, my little pickup truck, and then I ran the cables through the nice little sliding window in the back there. So I used the guide that comes with the system to lay out the two antennas exactly 800 millimeters apart, and then once I'd done that, I mounted this onto the rail and ran the cables through the back window. Connected them in, and once I connected them in and plugged in the power to the eDAQ, then I'm looking for the stat LED, which now tells me whether or not I've got signals from satellites, the status of the system. But keep in mind that as with all GPS systems, the eGPS200 may take a few moments to get the satellites that are in its line of sight. And of course that also depends very heavily onto the quality of sky and the relative location. If you're in a location where there's a building potentially blocking some of the view, it's probably worth moving. The yellow LED will actually illuminate, possibly blink to indicate that you have actually got acquired satellites. Now to actually look at them, we can do them fairly easy in TCE. Now it's a good idea, if you don't get the LED coming on, to just check your location of the two antennas. And remember that one is trailing, so this would be 1, this would be 2, and with the strip, the little guide, it's actually magnetic, so you can put it over the radius of the roof without any problems. And this is an excellent location because it's the highest point on the vehicle. It's not being subjected to any thermal effects from the engine, and I'm not suggesting that that will damage them, but the heat of the hood may cause adhesives to fail. So just keep in mind that this is probably the best location to get them anyway, the highest point on the vehicle, better line of sight. So do that, make sure you're in a good location, give it a few moments, and the yellow LED should come on. So moving into the software side of things, because it's designed specifically for the eDAQ Plus and light systems, it is a true plug-and-play system. All you have to do is query your hardware the same way as you would for any other configuration you're doing. Once you've queried the hardware using the query button here, you simply configure the GPS to use whichever one you have, And in this case, the example is the plus unit. So by double-clicking on the entry in the list of hardware or clicking on the config button, I can bring up the dialog that allows me to select the relevant GPS system. This is the RTK Plus unit. This is the standard 200, eGPS200, and this would be the 5 or 1 Hertz GPS using the NEMA standards. So in this case, it was the Plus. Double-click or config button, select this, OK, and now it's just a matter of adding the transducers in. So these are already predefined by that selection. So looking in the transducer list, we select the GPS from the COM layer, and then we get presented with all of the channels that are available for that particular interface. In the case of the Plus, obviously, we have all of the pitch roll rates as well as the yaw rate. So there is a little bit more in that one than what there is in the standard 200 that's going to give you much more accurate measurements for things like brake testing and performance testing. But selecting the channels, very simple. You could highlight all of them if you want. Some of them are less meaningful than others, but you select them, add them to the list, and just by nature of the design of this particular interface, you should always remember to, while still selected in the list, to edit them and modify the query and sample rates so that the query and sample rate is set to the desired rate. In this case, we can go all the way to 200. Some of the channels, the GPS channels, are in reality only 20 Hertz, but all of the RTK components are 200 Hertz. And if anybody tells you that a GPS system uses more than 20 Hertz, there's a high probability that they don't know what they're talking about. All channels can be checked by using the DVM or the scope. So you can just check to see if they're working okay. Of course, when you use the digital reader, it's a little bit easier. And just remember that you have changed it to 200 Hertz possibly. Some of the channels obviously can be ignored when you actually want to record them, which is done through button F4 in TCE. And again, in this example, we've taken the simplest one, time series recording, add time series, selected all of the channels, in this case all 29 of them. But of course, some of them don't really mean a great deal. There is one here, for example, says FAA mode. Fixed quality is actually quite useful, but you might not want to record things like nanoseconds, perhaps even seconds, or even any of the references here unless you want month and day, because the eDAQ generically already has available some of these components, so you really don't need to double up on them. But nevertheless, they are there. And in this case, all we've done is call it, in this case, time history, eGPS200, TH, time history. No trigger in this case because we're just going to record everything. This would be a classic kind of proving ground application, and then we're just going to record everything directly to the PC card. At 200 Hertz, we can get an awful lot of data. So, for those of you that don't remember this, and I'm sure anybody who's ever used an eDAQ before will be very aware of this, but the sequence, arm your system, which is basically initializing the test. Start your test run with the button number 3. View the data using the button with the number 5 on it. Stop the test run using the button with the number 6 underneath it, the little red light. And then upload the data for viewing using number 7. And then this example here is some data that I recorded on that same installation of that vehicle. And literally within 10 minutes of installing this, I was looking at data. Luckily no police officer saw it, so I shouldn't get a speeding ticket. But here's how simple viewing and handling data is with the infield software. And remember that the infield viewer is free of charge. You just simply load up the channels into the channels list, and in the viewer option you can just copy and paste it directly into Excel, or in the full versions you can actually save it in ASCII file format, in DeLorme, Microsoft Streets and Trips, verbose ASCII, and so on and so forth. Of course, you can visualize the data as well. This is an XY plot of longitude and latitude, and you'll see in a moment how accurate this is. And this is actually latitude and longitude just in strip chart plots. So you can view it, check the integrity of the data, and export the data very, very simply and quickly. So if you wanted to put it into something like Google Earth, this would be the first stage to going towards putting it into a KML format, which is the standard Google Earth format. And there are a number of websites that actually have the facility for you to just simply download this data as a textual data set, and it will actually produce the KML file for you, so you don't even need any fancy software to do this. This is just to demonstrate how quick and easy it is to just provide or produce reports to show people. So just a couple of quick steps. Here I've used the export active plot in infield in the plot window to export it as a meta file. So I've saved it as a meta file. I've specified some dimensions for the meta file. This is actually that very meta file exported and put into Microsoft PowerPoint. And then once you've got the references for the latitude and longitude, you can then go onto Google Earth or Google Maps. And in this case, I picked up the satellite view, and I've actually then used these coordinates to pick a section of the data out. And now in this example here, I've actually placed that data from the meta file directly on top of the Google map. Since this is completely transparent here, put it directly on top of the Google image here from Google Maps. And this particular bit that you're seeing here was me doing some figure of eights in a parking lot, and that's this chunk just here to give you an idea of scale. So it's actually that bit just there. So it's a very, very small fraction of the whole data set, but you can see very clearly the kind of accuracy level we've got here. This is the entire plot area, again, with the Google maps placed underneath it. And here we've got a little bit of the events that I created while I was moving around, and you can see here, in this particular case, this is kilometers an hour, so I'm only just over the speed limit. And you can see here a fairly hard braking event, and there is my pitch reference to that. This was actually moving over the dirt and going slightly faster, so here you can see the actual event correlated to the point in the data series. So very quickly you can put the plot for reporting purposes into some graphical representation of it. This is the zoomed in part of the same thing, and here you can quite clearly see the figure of eights. And it leads back to that illustration at the beginning of the 3-meter accuracy, that you can clearly see that the 3-meter accuracy is actually quite wildly greater than it can be. This is an example of using Glyph Works to handle the data, and in this case there's actually video data that's been put into the same data set here. So the video data is generically correlating with the GPS data, because it's all being recorded into the eDAQ, as well as other data from other sensors. In this case, the display is showing the Google Maps representation of the track, which is tracing around, and you can clearly see as it traces around, you can correlate that with the video images that you've seen, and you can see that this is a pretty accurate representation of the position of the vehicle, even though the weather conditions, as you can obviously see, were not the best for an experiment like this. If it seems to pause momentarily, that's a relic of PowerPoint, not the actual process, because this is constant and smooth. The displays down the bottom are the Glyph Works displays that can be added in so that you can actually replay, using the play option, some of the data. Some people may have noticed that some of these were jumping around a little bit at the start, and you'll also notice they jump around a little bit when it goes static. That's because in view of the weather condition and also the fact that it hadn't acquired the exact position, it got a little random at times. But you can clearly see here that correlating the data between both GPS, video, and other signals with eDAQ is very, very simple and straightforward. And Glyph Works is an excellent tool to use for the purposes of replaying and reporting. This is just a quick look into the brake testing aspect of the usage or the applications that you could use this for. The image there was of a military vehicle, a personnel carrier that was used for a brake testing test that was done in Switzerland. And of course the important thing is knowing exactly when something was instructed to stop via a pedal or whatever else, and how long it took to actually do that stop. And of course that's not the end of it, because there is other information that's necessary. We need to know the inertial component for this. We need to know what the yaw component on the vehicle was and how that affected the handling of the vehicle in the event, and how the mass was distributed as a result of any deviation from a straight line. So these are all the pieces of information that you can extract directly from your EGPS200. And because it's so easy to integrate with the eDAQ, it means you could be acquiring data using this for brake testing in fairly short order. If you prefer that you have the ability, or you prefer to do the calculations for your brake testing almost on the fly, and I say on the fly, they are actually on the fly, but you have to review them at the end of it, then you could even do that because the eDAQ is more than capable of running all the computations that are necessary in order to get rid of those derivations. In fact, if we move on a little bit here, this is an example of a brake testing configuration, and these are just the computer channels. And you'll see here that the computer channels need things like trigger components, speed components, pressure components for certain aspects of the operation of things like levers and pedals. Also other markers, perhaps if there's an ABS sensor and so on and so forth. And then the all-important integration for getting distances and so on. So you can see here that the speed monitoring method is triggered from a trigger. It could be triggered from a trigger at both ends. The trigger goes into the same end of the panel on the eGPS as the eDAQ connects. It's just a BNC type connection. And you could use the trigger to either initiate the event or even control the event complete. Or you could use speed components as well, which could be based on that GPS to a near zero, because it's almost impossible to guarantee an exact zero because of the wandering effect of GPS. But combine that with other factors such as ABS sensors and such like, and you can have a very, very accurate stopping point. And the eDAQ can do all of this processing in real time. In fact, some of these channels, as you'll see here, is some of them are actually phase delayed. The phase delay is so that we can actually look for that initial trigger moment, which is when the speed starts to decrease. The moment the speed starts to decrease is the trigger component, and then as soon as that occurs, that becomes a falling edge. Once there's a falling edge on this, that's the trigger. Once we have the trigger, we can combine that with other triggers as well, such as we can compare and make sure that the brake is being applied, either by the lever or by the pedal, depending on whether it's a motorcycle application or not. And once that happens, then we can say the test is active. And once the test is active, we can start integrating distances so that we know what the distance is, and we can start measuring, and these can be the triggers to measure the speed dissipation over the length of the event, as well as the pitch component, so that we know what the inertial component was. So as far as eDAQ is concerned, from a simple Boolean to a multi-order polynomial, it can all be done inside the unit. The green LED on the end of the unit by the antennas is the indicator for the trigger condition to be true if you want something to reference whilst actually doing the test. This is an example that is very important that I mention that this was actually created by a customer for their application. This was not created by us. This is something that a customer has done for themselves using the eDAQ API. And the eDAQ API can be used to generate custom or defined test routines, if you will. And this is just a flow chart of the components that are required in order to satisfy things like the federal testing requirements for the first and third effectiveness and so on. So this is all linked in to the eventual control mechanism that's written into the eDAQ. This software still generates a TCE file in the background, and once the TCE file is on the system, it then just works in conjunction with this interface here, so that the operator can see if they failed the test, if they're within the boundaries of the test, and if they've succeeded at completing the test, they get both of these. But again, I'd like to emphasize that this is something that was created by a customer, and we are just showing you what can be done. I hope we covered a few things that are beneficial to people, and that you are interested in looking at more of the EGPS200, and we can get our guys out there to demonstrate this to you at the earliest possible convenience. Thank you for your time.
Well, I do have, if anyone has any questions they would like Dave to answer, you can type those into the Q&A part, that interface in WebEx. Dave, one question came in the middle, asking, what does a 1 hertz flashing green light represent? I'm guessing they mean on the eGPS if the green light is flashing instead of solid.
Yeah, it depends on the revision of the unit. If it's an earlier revision, it may be flashing just to indicate that it's powered up. Some of them are solid and some of them are flashing. Either way, if the green LED is on the power line, on the power LED, that just means the unit's powered up.
Okay. So it's not an indication of a problem if it's flashing instead of solid.
No, and neither would be the yellow light flashing. It might be that it's still acquiring satellites. It's not a problem necessarily.
Perfect. I will be sending out Dave's presentation in PDF format to everyone who has attended here, and I will also send you a link once we have it posted on our website where you could revisit it. Dave, another question. Is there any hope for a higher G-rated product?
A higher G-rated product. I have to probably get an idea of what that actually is, higher G. This one is the measurement range of the plus is 6 Gs. Typically, when you're doing, unless you're doing impact tests, that's more than enough. So we probably need more information on that.
All right, I can put you in contact with the person who asked the question.
Wonderful.
Any other questions here today? A list price for the eGPS 200 plus.
Absolutely. Mr. Foxman would be more than happy to answer that question.
All right. We'll be sure to get you a quote. Can you explain the trigger connector? New question.
It's the trigger connector is just a BNC type connection, and it is literally just a state change. It is a state change. It's either open or it is closed.
All right. Well, everyone, we appreciate your attendance today, and as I said, we will send out the presentation so you have it for reference, and we'll send you information for it being posted on our website. Dave, thank you very much.
Thank you. Thanks, everybody.
Have a good afternoon, everyone.